Hello everyone, welcome to our QSI seminar. Today we have Kamil Korzekwa from Faculty of Physics, Astronomy and Applied Computer Science from Poland, and Kamil will talk to us about the fundamental constraints of quantum thermodynamics in the Markovian regime.
Thank you very much. Thanks for the invitation. It's very nice to be back in Sydney again, even if it's only online. Yes, so today I would like to tell you about some constraints that we found on the evolution of quantum systems in the Markovian regime. And this work was done, let's see if I can click it. Yes, this work was done in collaboration with Matteo Lostaglio, currently at QTech in Delft. And well, the outline of my talk is as follows. I will start with a few words of motivation. Then I will formally state the problem that we want to attack. And then I will proceed to describing the main technical tool that we have introduced to solve this problem. And this is the concept of a continuous thermo-majorization that I will describe in a little bit more detail. So for those of you not familiar, this may be a little bit boring part maybe. But then I will pretty quickly go to the results and explain what this technical tool allowed us to achieve. And this will be followed by the discussion of some of the applications of this result to interesting thermodynamic problems like optimizing some thermodynamic protocols. And finally, I will give some outlook for future work. And as I said before, but I will repeat, if you have any questions on the way, please just unmute yourself and interrupt me at any point, because I don't want to lose any of you on the way. Okay, let's start. So I will start with asking the very simple question, which is, what can we say about the dynamics of a system, whatever, quantum, classical, without solving the equations of motion? Like without actually solving, like taking the particular model and solving everything for the time evolution of the system's degrees of freedom. Well, for closed systems, it's we have things called conservation laws. So, for example, if you consider a harmonic oscillator with the classical harmonic oscillator with 2 degrees of freedom, I mean, in one dimension, the momentum and position. And you don't really need to solve all the equations of motions to know that if you start in a given P0, X0 here, can you see my cursor? I think so, right? If you start somewhere with P0, X0, you don't really need to know how it's going to evolve in time to be able to say that at any point in the future, it's the position in the phase space is going to be restricted to this ellipsis, which is basically the fixed energy submanifold of this whole phase space. So we have conservation laws for closed systems. For open systems, when our system that we focus on interacts with some environment that we don't have access to or we can't describe, it's a little bit more complicated. But still, we have some concepts and ideas like entropic production. You know, that the basic example is that of particles in a big box that are, let's say, initially or concentrated in one corner of the box. And we know that they can spread all over the box, but the reverse process does not happen. I mean, statistically, of course, and so on and so forth. But we can as well say some things. Or maybe the other easier example here is if you put a hot body next to the cold body and you connect them, it's not possible that at the end the cold body will be colder and the hot body will be hotter. That's one of the formulations of the second law of thermodynamics. So, okay, so those are those simple examples and motivating examples, and why I describe them is because quantum thermodynamics tries to or aims at using some minimal assumptions of the quantum theory and trying to find the constraints of the evolution of quantum systems interacting with thermal bulbs. So now we don't think about closed systems, we think about open systems. Our system is a quantum system, a finite-dimensional quantum system usually, and we try to understand what can happen to the system. We don't want to exactly solve, let's say, I don't know, an atom interacting with a single bosonic field and then exactly know the time evolution. No, we want to have a rather general model, maybe not model, a rather general description for many, many different models that will tell us what things can and what things cannot happen in the future without exactly solving the equations of motion. Let me just check chat because I was told that maybe some questions are here. Oh, sorry, that's not for me. Okay, so so we know what the quantum thermodynamics is trying to study, and let me just be a little bit more precise with that. So what kind of problem we try to solve is that of a finite-dimensional quantum system, initially in a state described by a density matrix rho at time 0, and it can interact with many different heat buffs. And when I say many different heat buffs, I mean each of these heat buffs is an arbitrary quantum system, meaning arbitrary Hamiltonian, as long as it's prepared in a thermal Gibbs state with respect to the same temperature or inverse temperature beta. And we want to ask what can be the possible states of the system of interest at some later time t f time, final time. And this question was originally asked already. I mean, I think it was asked probably many times, but in the resource theoretic description that we're going to use, it was probably first asked in 2013 by Michał Chorzecki and Jonathan Oppenheim, where they studied exactly this kind of problem, where these arrows here, when I say, because this represents interactions, so they were considering this to be arbitrary energy conserving, total energy conserving unitaries. So basically, this gave rise to the so-called thermal operations. So any kind of quantum channel that transforms this rho 0 to rho TF that arises from unitarily interacting with many buffs, such that this unitary interaction conserves the total energy. This is called thermal operation. And this guy studied this and got some nice results there. However, let me point out that although the results that they obtained gave ultimate restrictions on what can happen, they didn't really describe what thermal buffs are. Because when we think of thermal buffs in the traditional picture of open quantum system dynamics, we think of buffs being big systems that are much bigger than the system of interest, and such that the correlations quickly decay. So here, actually, when they solve this, they allow for creation of any kind of correlations between the system and the buffs, and then they can reuse those correlations later. Basically, the buff could act as part of the buff could act as a memory. So this was definitely a nice result and of fundamental importance. But the way the interactions with the buffs were modeled were a little bit not physical, but like not really applying to most cases of interest. So what we are thinking was whether we can improve this question that they asked and do this for a little bit more physically motivated scenarios. So now what we ask is like exactly the same kind of question, the same kind of setting, but now those arrows do not denote arbitrary energy conserving unitaries that can lead to arbitrarily strong non-Markovian effects and so on and so forth. But basically those arrows are just Markovian energy conserving interactions. So Markovian here meaning, I'm going to just in the next slide explain what I mean here, but for those of you that want a simple one sentence explanation is, well, those are memoryless things. So anything that happens, these interactions are such that whatever happens at one moment in time when they thermalize, it does not affect the other. I mean, at each time, it's just this system doesn't remember its past. I mean, those interactions do not depend on the past. Okay, so now to be even more specific, let me formally state the problem. So we know that the general Markovian open quantum dynamics, so this memoryless open dynamics, is given by the Lindblad equation, where we have the evolution of the system, the time derivative of the quantum state is given by those two parts. The first part is the unitary evolution, is the closed evolution. This is the Hamiltonian of the system, or the dressed Hamiltonian of the system. Whereas this is the dissipative part. Okay, let me just dissipative part described by Lindbladian. Those we exactly know that this is the most general thing since the 70s. This is the Lindblad, Gorny, Korzekowski, Suda-Sharan equation. Let me just point out that, so that we remember that EIs from now on will denote the energy levels of the system. As I said, we consider finite-dimensional systems, so the dimension is going to be set to D. And okay, so this is general Markovian open quantum dynamics, but it's not yet describing the interaction with a heat bath. It can be anything. I mean, the external environment could be anything, not really thermal. So we define the Markovian thermal process by our additional two properties. First of all, we require that in a long time evolution, systems have to thermalize, meaning that the thermal state is it's in the kernel of the Lindbladian, which basically means that it's the stationary state of the evolution. Thermal Gibbs state given here, the standard expression for the thermal Gibbs state. And second of all, we consider covariance of the Lindbladian, so that it kind of commutes with the commutator with Hamiltonian, and that encodes the total energy conservation, again, as with the thermal operations. The natural extension of those thermal, oh, my connection is unstable, that's not nice. I'm still there, right? I hope. First of all, this is the natural extension. Yes,
sorry,
yes.
it may be the last minute because you froze there for a bit.
Yeah. That's so weird. I'm so sorry. So where did I froze, with the general Markovian quantum dynamics, or? Hello? Yes. Am I with you still? Sorry, I mean, that's weird.
Right when you were asking where you left off.
Okay, so yeah, maybe just.
It's a good place. Yeah, this is fine. Yeah.
That's good. Okay, so very quickly repeating, stationary thermal state and covariance, which encodes energy conservation, and then those two comments. One is the microscopic derivations of Markovian open dynamics with particles in normal systems usually lead to those kind of conditions, that the thermal state is stationary and we have covariance. That's from weak coupling regime. It's coming from the weak coupling regime. And the second is that this is the natural extension of thermal operations to the Markovian regime. Okay, so what we want to solve now, well, we're gonna say, okay, so this gives us the Markovian thermal process. So Markovian thermal process is any quantum channel that arises from integrating this kind of equation with Lindbladian satisfying those two parts. And
excuse me, can I ask a question?
Of course, yes, please.
Sorry. Hi, Kamil.
Hey, Daniel.
So you allow time dependence of the generator, but only on the rates, but not on the jump operators, and not on the Hamiltonian part. Do I understand that correctly?
Yeah, well, okay. So I have to be a little bit more specific here. Yes. So well, okay, that's a very good question. So basically, yes, not on the Hamiltonian, even though, as you will see, our framework will allow you later to intertwine like Hamiltonian change and then Lindbladian, Hamiltonian change and Lindbladian, because this is a framework maybe suited for like heat engine stuff when you have different strokes, when you connect to the heat baths and then you do something. We didn't want to allow for the change of Hamiltonian, because change of Hamiltonian usually means you have to perform some work. And those, in this resource theoretic approach, you really want to think, like you really want to account for every kind of input from the outside. So that's one thing. Whereas this guy, this time dependence, yes, it looks weird, because what does it mean? Well, as you will see, all kind of time dependence in the end, as we'll prove, just account for being able to switch on and off interactions. So if I just go to this guy, it's going to be like I interact some two levels with some bath, and then some other two levels with another bath, and some other two levels with another bath. It doesn't have to be really like complicated thing. It's actually just switching on and off interactions. So you take a system, you don't really change its Hamiltonian or anything. You just couple it to different buffs at different moments. So it looks a little weird that we have this time dependence here. But the only thing that actually, you will see that all those kind of time-dependent Lindbladians can be just generated. I mean, the evolutions from all those time-dependent ones can be generated by just very simple time dependence of just coupling at some point to one buff, at the other point to the other buff. So,
okay, but I mean, I guess my question then is, are you given these LIs at the beginning as part of the problem, or
no,
are they completely arbitrary and
yes, no, sorry,
necessary because you can always map it into...
Yes. So actually, I guess I shouldn't write d squared minus 1 here. It could be like infinity here. And this way you can turn on some Lindbladians and send some Lindblad operators and then turn them off. No, you are not given them at the beginning. You can choose whatever you want.
Okay, and my second question, if I may, then
yes, of course.
That the steady state should be the Gibbs state. Are you allowing for other steady states as well, or is this the unique steady state? Because you could have, for example, the identity map has the Gibbs state as a steady state, but many others as well.
Yes, well, we do not need to use the assumption of having other or not. Like, as long as this Gibbs state is the thermal Gibbs state, we're gonna have our constraints. I guess if you add more fixed points, you would even constrain more. But whatever we're gonna obtain is gonna work for all those cases.
Okay, thanks.
Thank you very much for the question, and I encourage others to also interrupt me if some things are not clear. Okay, so let's get to the problem. So now we know what a Markovian thermal process is, right? Yes, please.
Yeah. So just when you say you're solving for the possible final states, I just want to be clear, like what's like the thing that you're producing at the end of this to know that you've solved the problem. So are you saying that you want like the entire evolution path, or like for a given, or is that you're also given some set of final states and you just want,
Exactly. Yes. So you will see. So the ultimate goal would be for every state raw, we would like to produce the so-called future thermal cone, which is a set of states that it could possibly evolve into. Right? So we don't need the full path. I would like to have a mapping between the set of states and subsets of states where they can evolve. So I would like to be able to predict what is the possible future and what is for every state.
Okay, so the idea is that, like, given a state and given a master equation, you're going to come up with that like one-dimensional path of like evolution, and you don't actually care like when it gets to certain points. You just care about like what's the shape of the overall one-dimensional path.
No. There's not a one-dimensional path. I don't care about the path. I only care about the endpoints. I only care about the so there is basically from raw zero there is infinitely many different paths coming out from raw zero, each one corresponding to a different Markovian open quantum dynamics, and they can all end up somewhere. Like one of them would be the identity map, so the environment is trivial, there is no environment, so this path is basically just staying raw zero in raw zero. Then some other paths will be going straight away to the Gibbs state, like in the closest route possible. And we just look at all the possible endings of all the possible paths, and this is our set.
Okay, so the idea is that you're looking for the set of states that can be reached by these dynamics given some T sub f. So it's not that you're given T sub f, it's not even that you're given the dynamics, it's you want to know what's even reachable with this. Okay, I think I understand.
Yes, okay. Perfect, thank you. I hope that also clarified things for the others as well. So this would be the perfect thing if we could do this for all states. However, we're gonna solve a little bit more constrained problem. You're gonna see in a second. So this is solving for all possible final states would be our best thing that we could aim at. But let's see what we're gonna do with that. So let me know that this covariance property that we have those two properties. One is the fixed thermal state, the other is covariance. So covariance actually gives us the separation of the evolution of the populations in the energy eigenbasis. So populations in the energy eigenbasis are just the diagonal elements of the density matrix in this energy basis. And coherences, I will refer to them as the off-diagonal elements of the density matrix in this basis. So those guys evolve completely independently, meaning whatever the coherences whether they were zero or some non-trivial superpositions of states, it doesn't affect the evolution of populations. So we can decouple them, and what we're gonna focus is actually a part of the solution of this problem. Like, I mean, the full solution of this problem would be any kind of density matrix you give me. I can tell you all the final density matrices. Whereas what we focus on is you give me the populations in the I mean energy populations, so the diagonal of the density matrix, and you ask where can it go. Well, to be more specific, we can actually, because we solve even a more general problem, which is you give me any initial guy, and the final guy has to be diagonal. You can think of it this way. But in general, what we are looking at is not evolution of superpositions, but evolution of populations in the energy eigenbasis. Okay, so if we have this simplified problem, then, well, we can rewrite this original V rho of t, this original Lindbladian, in a much simpler form as the evolution of the population vector, energy population, with this L of t having some. This is like the generator of a stochastic evolution, stochastic matrix. So when you solve this, you find out that the possible final populations are, well, this is a vector, right? This is a vector of populations. It's just a vector of d numbers that sum to 1 and are all positive. So the possible final populations, when you look, it definitely has to be some t times p0. T is a stochastic matrix. Any mapping between one probability vector and the other is a stochastic matrix. So it has to be definitely such a thing. And it's going to have two properties. One is stationary thermal state. Well, it arises from this condition, of course. And the other is this embeddability, which is basically that, well, it has to arise from a Lindblad equation. So it is, it satisfies this kind of differential equation. It doesn't matter, that's maybe a technical thing. The important point is that, well, we have to find all populations that look like TP0, right? And they have, and those T is not all stochastic matrices, but those that satisfy those two conditions. So the conditions for the first one are known. And this is exactly from this paper by Hordetsky and Oppenheim. And solution to this first constraint is known as thermo-majorization. I'm going to describe this in a second. So basically what our work, our contribution is how do we generalize this thermo-majorization condition to also account for the fact that those stochastic matrices are embeddable, so like Markovian or memoryless. And solution to a set is known as thermo-majorization, meaning that it is known that there exists a T such that it maps P0 to some PTF and also has a stationary state gamma, if and only if the original population thermo-majorizes the final population. Okay, so if not for the Markovian condition, or the fact that there is this embeddability condition, we would already know what are all the populations that can be achieved from some given population P0. They would be namely all the populations that PTF that are thermo-majorized by P0. And when I say thermo-majorized, okay, that sounds weird. Let me just have one slide to describe how do we verify the thermo-majorization condition. Well, thermo-majorization is a generalization of something called majorization that I guess most of you, being in quantum information community, have met already. So majorization is like you have two vectors, you arrange them in a non-increasing order, and then you look at the partial sums. And this is, I think it was popularized by the Nielsen's theorem, because this was a condition for the entanglement transformations under LOCC for pure state, for pure bipartite entangled state. But thermo-majorization is a little bit more complicated. So what do we do here? How to verify this condition? Well, first of all, you have to find something called gamma ordering. So you don't order them in a decreasing order, but you actually arrange not PIs in a non-increasing order, but rather you arrange PIs rescaled by gamma i's, where gamma i's are the thermal state occupations. So let me just use this three-dimensional system as an example. A three-dimensional system, I mean, so this is in this triangle, you have all possible populations of a three-dimensional system. So here is the ground state, here is the first excited state at the vertex, and here is the second excited state. and all the other points are convex combinations. For example, here in the middle between those 2 points would be 1/2, comma 1/2, comma 0, right? And here I chose this gamma to be the maximal unique state. So actually this thermo-majorization here is majorization. So you divide this simplex into pieces in which things are ordered. So in this piece, the first entry is the largest, the second largest is the second largest, the third entry is the third largest. Here, for example, the third entry is the largest, the second is the second largest, and the first is the smallest. Okay, so once you ordered your piece, your piece. Let's say I'm going to focus on this guy. Let's say the P has this ordering. So P2 is bigger than P3 is bigger than P1. So well, actually, P2 divided by gamma 2 is bigger than P3 divided by gamma 3 is bigger than P1 divided by gamma 1. Then you have to create something called Lorentz curves, which is like once you have these guys ordered, you just on the X and on the Y axis, you put these partial sums, very similar to majorization. So on the y-axis, you exactly the same kind of thing. You put those guys in a non-increasing ordering. Whereas on the x, instead of just putting 1, 2, 3, you put the Gibbs occupations. So in this example, let me just show you how it works. If I have a p with this ordering, so p2 is larger than p3 is larger than p1, then what you do is you first take p2, and on the y-axis you put p2, on the x-axis you put gamma 2. Then you look at this, what's your ordering? It's 3 now. So now the next point is going to be p2 plus p3, and here gamma 2 plus gamma 3. And then finally you also add gamma p1 and gamma 1, but it's normalized, so it adds up to 1. So you create something like that, and that's called a Lorentz curve or thermo-majorization curve. And this, you also do this for Q. Right? I mean, we just did it for P, for the initial state. Now we do it for Q. And if the whole Lorentz curve of P, like here, lies above the whole Lorentz curve of Q, then P thermo-majorizes Q. Otherwise, if they, let's say, intersect somewhere, so neither one lies all over the other or the other all over the first one, then there is no thermo-majorization condition. So that's basically, you see, that somehow ordering all distributions in the space of distributions it's putting some kind of partial order, and this is exactly how to verify it. And this ordering was shown in 2013 to describe population dynamics when you use thermal operations, so the ones that I told you before with arbitrary non-Markovian effects. So what we did is, well, we introduced this concept of continuous thermo-majorization. It's a very straightforward extension of this concept that we are actually surprised that we couldn't find any kind of this extension in the literature, even though there is this famous book by Marshall and Olkin on all kinds of majorization and generalizations, 1,000 pages book, and they didn't have this continuous version, which was surprising. So what's continuous thermo-majorization? Well, we say that a given state, P0, continuously thermo-majorizes PTF, if and only if there exists a term, we call it thermo-majorizing trajectory, so like a whole family of states P of T, such that thermo-majorizing relation holds all the way along the trajectory. So maybe a graph will be better. So P0, Markovian thermo-majorizes PTF, if and only if there is this path, this trajectory connecting them, and such that for every point on this path, and for every 2 points, for every 2 points in this path, like here, the point that is further in the trajectory is thermo-majorized by the point that is before. So we have like basically we have thermo-majorization condition all the time and the force continuously over the path. Well, that's why the name continuous thermo-majorization. And the reason is, well, we can already guess, I guess, why did we introduce such a concept? Because we are able to prove that this actually yields a complete description of population dynamics. That is, if you want to find all those final, given initial state, all the future thermal cone achievable by all possible Markovian thermal processes, this condition is exactly equivalent to the condition of finding all PTFs, or all final distributions that are continuously thermo-majorized by P0. Okay, so this is the first starting point. I mean, we could end here, but then this would be useless. I mean, you could come and say like, okay, you just rewrote this thing using different conditions, but like, how do I even verify this, right? Like, it's really hard if you think in the first place, like, how do I verify? I would have to, for every 2 points, I would have to look for all possible paths connecting them and try to find the path that is all the time thermo-majorizing. So we weren't happy with that, and we worked a little harder, and we used this as our first starting position, let's say. And the results are as follows. Okay, so we build up a little bit. So first of all, maybe we rephrase this again in again not that useful formulation for finding all states, but it's useful for people who work in standard thermodynamics when they look in when they are used to things like entropy production relations. So what we were able to show is that this result before is equivalent to the following thing. If you have some dynamical evolution P of t, so you have some evolution of, you have a continuous path of evolution of populations, we say that it can be generated by a Markovian thermal process if and only if this family of, well, I don't know how to call it, generalized entropy production relations increase. Generalized entropy production relation holds. So there's a whole family of functions, a continuous family of functions that have to increase over time. The point is, obviously, it's not that hard to write a function that has to increase like that. These functions are called monotones in the resource theoretic picture. The important thing here is not that they are increasing. The important thing is that this is a statement if and only if, meaning that if you check that all of them are increasing, then you are sure that there is a Markovian thermal process generating this evolution. So it's not just that it's like necessary conditions, a necessary and sufficient condition. Okay, the next step was maybe will not sound that interesting to you, but actually this allows us to do the main contribution in the next slide. So the next step is, well, we also were able to prove that you can go from P0 to PTF by a Markovian thermal process, if and only if there is a sequence of elementary thermalizations, such that, I'm going to say in a second what's a elementary thermalization, basically that P0 can be brought to PTF by a sequence of elementary thermal operations. There's thermalizations. What's an elementary thermalization? Well, it's an operation on the population vector such that it doesn't touch almost any vector. So this is identity on all levels but I and j. So it doesn't do anything well, it is trivial to all but two levels. And on those two levels, it does a very simple thing. It's basically just thermalizing them, bringing them closer to the thermal state. So yeah, so you basically take the spectrum of your system and you just couple two levels to the heat bath. I mean, and then maybe couple other two levels to the heat bath, and then maybe couple another two levels to the heat bath. And okay, so two comments here. One, it's quite interesting from the perspective of control theory that any kind of control over the Lindbladian that you can have there, all complicated functions of time dependence and so on and so forth, can be actually, when you focus on state interconversion from initial state to the final state, all of these things can be achieved by simply just coupling at any given moment two levels. Two levels, let's say couple 1 and 3 and thermalize them a little bit, then couple 2 and 4 and thermalize them a bit, and then couple 1 and 5 and thermalize them a bit. And this way, by these controls, you can achieve all possible transformations that can be done by Markovian thermal processes, at least when it comes to population. And second comment is, well, actually, people who know a little bit of majorization theory know a similar result. So in majorization theory, there's a result that if P majorizes Q, then you can go from P to Q by a sequence of something called T transforms. And T transforms are exactly this kind of things, just for the Gibbs state being a maximally mixed state. So it's just mixing them exactly. And interestingly, when people try to extend this result from majorization to thermo-majorization without the Markovianity, they found out that this is not possible. That actually, when you do thermo-majorization, there are some cases where going from P to Q requires you to couple all levels of the system, all D levels at once, because otherwise you you will not be able to achieve some transformation. So what we are showing here is that when you enforce the Markovianity condition on top of this thermo-majorization thing, then this complicated picture of coupling all levels at the same time simplifies to the picture that we know from majorization. So you just need to couple only 2 levels at a given moment in time. Okay. Are there any questions? Okay, that's good. I think we are good with time. So having this, we're able to prove our main result, and our main result is basically algorithmic verification of the condition whether there exists a Markovian thermal process mapping P0 to PTF. And what this kind of algorithmic verification has is, first of all, it's always only a finite set of conditions needs to be verified. And when I say finite, I don't say like continuous family of monotones. No, like 10 or 15 or 11. The same way as checking whether this guy is above this, just checking the conditions, or actually D-1, where basically you look at the elbow points and check whether they are above. The same way we have a finite set of conditions to be verified for the Markovian thermal process to exist. Moreover, if you verify this and the conditions are hold, so there is a Markovian thermal process, then the algorithm gives you exactly the Lindbladian realizing it. So we exactly give you what kind of process can actually move P0 to PTF. And a slight modification of this algorithm actually gives you the full set of states achievable via MTP. I mean, the full set of states, again, not states, populations. So not only verifying whether P0 can go to PTF, but given P0, I can give you the whole subset of the simplex that you can reach by Markovian thermal processes. If you are interested, this is freely available at my GitHub. I mean, the algorithm, you can just download it and it works mathematically. There's just a function that does it. So let me just say how is this done. I mean, obviously that's the main guts of the paper and the technical contribution, but the simple ideas, the ideas are not that hard. So first of all, so there's 3 ideas basically, and first idea is, well, if the initial and final state, so P and Q, are in the same, remember those were those gamma orderings. So this is like the first entry bigger than the second bigger than the third, like Gibbs scale. And then those are different chambers, we call them chambers. So first is, if you have the same ordering, then the whole thing is easy. Because continuous thermo-majorization within a given chamber, within a given ordering, is simply equivalent to thermo-majorization. So if you are in the same if you are in the same order, if you have the same ordering, then thermo-majorization and majorization and continuous thermo-majorization are equivalent. And because thermo-majorization, you just need to verify D-1 conditions, then you just verify them and you are done. Okay. What happens when orderings are different? So when my P is in one chamber and Q is in the other chamber, what we were able to prove is that there is a unique optimal way of going from one chamber to the other chamber. So if I want to go from this guy to this guy, let's say, there is a unique way of doing this, and this is exactly the thermalization between the 2 levels, like this elementary thermalization that just touches 2 levels and does not touch the others. And actually, well, so then you go from one ordering to the other, then from this one to the next one to this one, and finally you get to the point where you know that this is the optimal point that you could reach going through this path in this chamber. Now you are in this chamber, so you just use thermo-majorization, which is shown here in this small triangle. And the third idea is, well, there is just a finite number of paths connecting different orderings. So here I could go either this way, or I could go this way. Of course, you could say, oh, maybe there is infinity many because maybe I can go here and then back and then here and then back. But actually, this is we prove that this is not the case, because obviously, if you enter twice the same path, the same case, basically the optimal paths are the ones that are just once in a given chamber. If you go there again, then yes, please.
Hi.
Hey, hello. Hey, Maria.
Okay, so I was wondering what these chambers are and what's the significance of making these chambers?
Oh, sorry, one more time. Yes. So I'm just going to repeat. So basically those chambers correspond to the so-called gamma ordering or beta ordering or thermo-majorization ordering. I mean, people call it differently. So it's basically, let me just go very quickly back. So it's basically what you do is you take your P, your initial state, or the final, and you Gibbs rescale it. So you divide every pi by gamma I, right? And so now you have a set of D numbers, and you try to arrange them in a non-increasing order. So you find out that, let's say, P2 divided by gamma 2 is the biggest among all others, Pi divided by gamma I. So the largest one will be the 2, and then let's say the next one is 3, and the next one is 1. So it's basically just telling you somehow a generalized ordering of your vector, right? I mean, if gamma is the maximally mixed state, then maybe that's the easiest way to think of this. If gamma is the maximally mixed state, which corresponds to the infinite temperature limit, this is basically the ordering in a non-increasing order, like the largest, the second largest, the third largest, and so on. So those orderings are basically whatever is here. All states here are such that P1 is bigger than P2 is bigger than P3. And all states here are such that P3 is bigger than P2 is bigger than P1, and so on and so forth for every.
Okay, thanks.
Cheers. So that's actually quite interesting to know that all the complication that comes from Markovianity actually appears at the boundaries, because within thermo-majorization and continuous thermo-majorization is the same. Only when you get to the boundary you have to hit, and then it changes. I mean, okay, I don't have time to show how this looks for a non. I mean, basically for a non-Markovian ones, you wouldn't have to stop here. You could go all the way here and then all the way there. But this is not possible with the Markovian thing because you can't keep the memory of where you came from. Anyway, that's let me get to. So actually, I'm going pretty slow now. There's still some slides on the applications. So basically let's just sum up this slide, and the main result is we give the equivalent of thermo-majorization condition for Markovian thermo-majorization. Equivalent meaning there is a finite set of conditions that needs to be verified, and there is the algorithm that does it. The only problem is the number of conditions grows much faster than in thermo-majorization case. There it was always D-1. Here it's starting growing with d factorial. So on a standard laptop computer, we are able to look at systems, let's say, of dimension 8. But to be honest, I believe that we can improve this significantly if we just get some maybe computer scientists into it, because we are just physicists and are not that great in optimizing algorithms. Okay. So let's try to apply this. So what do we apply? What do I mean by applying? Let's consider some standard thermodynamic protocol. And this one, yes?
Sorry, can I ask a question?
Yes, please.
This slide. Can
you
go back? Yeah, so you're verifying the continuous process, right? This algorithm is trying to verify a continuous process.
Whether they exist a continuous, Markovian thermal process, yes.
Yeah, so is there an intuitive way of understanding how you end up with actually just finite set of conditions that you need to verify?
Yes, well, yes, there is. I mean, this is well, okay. So first of all, we have to go all the way back to this main result, which is where there exists this this process if and only if there exists a continuous thermo-majorizing path. And now we simplified the problem of looking through all channels, Lindbladians, and so on, to simply looking at the existence of thermo-majorizing paths. Now, so this is one thing, like whether you can draw a path that connects one guy with the other guy, so that the thermo-majorizing condition holds for all along the path. Now, once you know this, you can simplify the analysis to understand, well, if I only need to look at the paths, maybe there are some optimal paths, right? Maybe I don't need to look at all possible paths, because maybe some paths are better than others. Unfortunately, I mean, well, that sounds bad, but yeah, there are. So basically what we say is, if you want to go for, so again, idea one, if you are inside, if your initial and final state are inside, then you don't really, the paths are really described by thermo-majorization, so there is no problem. But then if they are in different guys, so I go from P to Q, so there maybe there is a path like this, right? Like, sorry, like very curly path like that. That's possible, but like the point is that if I want to go from P to Q in a continuous fashion, right, there must be a continuous path. So this path will have to cross some borders. There is no way. We are in two different countries, and if I go from P to Q, I have to cross some borders. And now the result is, the thing that we proved is, if you want to cross a border, there is an optimal way of doing this. I could cross the border here, I could cross the border here or here, but all those crossings are worse than crossing from here. The reason being, when I say worse, I mean every point that can be reached later if I crossed here can also be reached when I cross here. So basically, there are just, from this whole continuous set, you can think of this as like from the set of all possible paths, we found extremal paths, and those extremal paths are actually discrete numbers. Right? There's a discrete number of those paths. Well, I mean, sorry, I mean, to be honest, you know, this is just a single slide to try to explain something that takes us like 10 pages in a paper. So, I mean, it's maybe, if it's not exactly understandable, I recommend taking a look at the paper when it finally appears on arXiv, hopefully within a week or two from now.
Yeah, okay, thanks.
Okay. Chase, thanks for the question. Okay, so what do we want to do with this? Well, so we have a framework. We have this algorithm that verifies what can be done and what cannot be done, and what can we do with it? Well, we are thinking, let's take a standard thermodynamic protocol like work extraction. So what's the work extraction? Well, you start with some system out of equilibrium and some ancillary battery system that is like in the ground state of its Hamiltonian. And your aim is to perform some interaction with the bath, you couple some bath to it, and at the end maybe equilibrate your system, but also charge excite the battery system to be, you know, to have some higher energy so that you can use it later. That's why it's called work extraction. So you extract work, like you have some out of equilibrium system that maybe is not really, you know, not like a work system, and then at the end you end up in a system that has a very well defined energy that is higher than the ground state. So how do we model such processes in the resource theoretic approach? Well, your system out of equilibrium has some population occupation or energy occupations. Your battery can be a single two-level system in the ground state initially, and we want to find a Markovian thermal process that maps it to the Gibbs state here, and something that is almost excited. This epsilon is like the failure probability of exciting this battery. So we can look at this, because we now know how to do this, right? I mean, we just said we have the algorithm to verify what is the MTP here. So we can change the energy gap here, and for each energy gap, so for each amount of work extracted, we can get the optimal epsilon. And then we can also compare it to the previous results with not Markovian thermal processes, but thermal processes, those thermal operations from 2013 I told you about with Michał Hordecki and Jonathan Oppenheim. And we can also try to check how much work you can extract in this case. And what you're going to have is a comparison between how much work you can extract from a system in general versus how much you can extract from a system if you are restricted to Markovian processes. So basically, you're going to get the improvement that comes from non-Markovian or memory effects. So here we have a simple example. So let's see what we have here. Okay, some system spectrum. Battery has a state 0 and W, and then the bigger the splitting, the more work we extract. Red is thermal process. So when we allow for all non-Markovian effects, we see that what's going on is you can extract more work for the price of getting some error. And then the more work you want to extract, obviously you get the bigger error. Whereas for Markovian process, not only it's much higher the error for every work, but also it doesn't even go to 0 when your work goes to 0. Meaning that for deterministic work extraction, you actually, or close to deterministic work extraction, you actually need memory effects. Second one, maybe role of memory in cooling. We can also study, well, if you can study every thermodynamic protocol, so cooling is one of them. So here we look at something called, or one step of something called heat bath algorithmic cooling. So basically, what heat bath algorithmic cooling is, one way of to see this is, you have a system that is at the thermal state with some temperature. It's in equilibrium with the bath, and then what you do is you pump it. So you unitarily invert its population. So you, let's say, the populations of the ground and excited state exchange, and now you interact with the bath and try to cool it below whatever it was there before. So let's say you want to maximize the ground state population. So again, we can try to study this with MTPs and TPs, and here what we see is, well, that's how much you can increase the ground state population in one step of such a heat bath algorithmic cooling. That's kind of dependence on different temperatures. And again, you see that with Markovian effects, you get much better than for non-Markovian effects. And basically, well, in zero temperature and in zero temperature there in the far right, and infinite temperature here, there is no improvement. But that's also easily understood why we don't expect the improvement there. Okay, well, in zero it's pretty clear. You cannot get below zero, right? In infinity it's a little bit more complicated, but it's also understood why. Okay, I still have not that many minutes, so let me just say that, well, we also can study the role of catalyst in thermodynamic protocols. So a catalyst is something that, you know, you want to go from P to Q, but you also add some C, and the C will be C at the end. So it's a catalyst. You bring it, it helps you do something, but at the end you get it back exactly. And we actually see that so this way we can study not only the memory, having memory or non-memory, but also to quantify how much memory we add. So here, for example, what you see is, like, you start with a system that is, I think, twice hotter than the you start with a system that is twice hotter than the bath, and you want to cool it down. And it's a qubit system, and you know, if there is just a qubit system in the bath, the final temperature cannot be cooler than the bath temperature. But if you allow for, if you do this in a Markovian way, if you allow for non-Markovian processes, you can actually cool it even more. And the reason there is obviously, well, if you have a system and you cool it down and you allow for some memory, while you cool down some system, you can, you know, it's like a heat engine. You can extract some work when you cool it down, put it to the battery, and then when your system is exactly as cool as the bath, you can use this battery to cool it down even further. So this is where you have the red curve. And then, well, the dashed line here is what you do if you have a Markovian thing, but you use a 2D catalyst. And this catalyst in the process basically acts as a two-dimensional memory. And you see that you can get better, and if you have bigger catalysts, you can get better and better and better. I mean, at least this is what we expect. We still have to do some simulations there. Okay, so let me go, 4 minutes left. So what do we want to do in the future, or what is there to be done in the future if you are interested? Well, first of all, let's try to apply our framework to study some non-Markovian boosts to relevant processes. We just analyzed those very simple ones like work extraction, cooling, but we just wanted to, you know, illustrate the usefulness of the framework. But hopefully there is much more to this. And there is this paper actually from Plenio group, Susanna Helga Plenio, and one of the PhD students probably who did all the work, but I don't remember his name. So they were using our framework to show the non-Markovian boost to the efficiency of biomolecular switches. And then we also would like to understand the asymptotic behavior of this continuous thermo-majorization. Like if you start having many particles, does this Markovian condition still restrict us so much, or maybe in the many copies of the system it simplifies somehow? That's quite interesting, because thermodynamics usually is done with many copies. You know, thermodynamic limit with many systems involved. Well, obviously, one would like to extend this formally to 3 states with coherences and understand how coherences can transform as well. And yeah, and number 4, which is probably the most important for applications, again, is optimize the runtime of our algorithm, of this algorithmic verification procedure. That is kind of an engineering task that we have to cope with. But yeah, I mean, it sounds boring, but actually being able to increase the system dimension that we can study could allow us to do much more. And this is gonna be soon on archive. We're just rewriting some intro, and it should appear within the next 2 weeks max, hopefully. And thanks for your attention, and thanks for the invitation.
Thank you, Kamil. I know that there were already a lot of questions during the talk, but we have a question from Daniel.
Yes.
Hey, thank you. So yeah, it looks very nice. I have a question regarding your fourth point. So you're probably very familiar with the work by Toby Cubitt, who showed that the classical embedding problem for a stationary master equation is actually empty-hard.
Yes.
So I was kind of expecting that in your talk, the embedding problem would pop up a bit more, but I didn't see it later anymore. Yeah. Are you able to avoid it because you're looking at time-dependent rates, or are you able to avoid it because you have this additional constraint of the thermal state?
No, I think I'm able to. I think I'm able to avoid it because I'm looking at input-output relations and not on the maps themselves. I don't care which map can be embedded and which not. I'm not looking at the stochastic matrix. I'm just looking at one state can go to the other state. That's a different.
Even for the input-output, it can be even worse, right? There is work also by Cubitt, and I think I forgot the other authors, but showing input-output of a given set of channels, with the question whether you can reach one particular mixed state from another one is actually undecidable. So again, you seem to avoid that as well. So you're very lucky, or maybe your algorithm is very inefficient.
Oh yes, okay. So I definitely have to take a look at this one then of Toby Cubitt, because maybe I have to go into the details of his paper and before we put our stuff on archive to be sure that that's not the case. Well, I think it is inefficient. I think it is inefficient in the sense that, well, let me just point out the thing that, yes. So here it looks very simple, right? I just drew two different paths going from P to Q because, you know, there's a very simple division into those orderings. But one has to remember that the number of orderings grows like d factorial, right? So as soon as you go, I said level 8, we did 8 levels, but for 8 levels, the number of those ordering boxes is already huge, right? 8 factorial is already a very huge number, and we try to analyze all possible paths going from one box to the other. So maybe we are fine because we are very, very inefficient. But yeah, I would have to compare with him. Yes, definitely. That's a very good comment. I mean, on the other hand, I would hope that there is a lot because look, imagine that I want to go from this chamber to this chamber. It's almost obvious that I should go from here to here rather than all the way around here, because crossing every border introduces a lot of entropy and like going from this to this, like to the neighboring one, the best way would be just to go straight to this next, to your neighbor, rather than go through all the other guys like that. And I think this is not gonna be rigorous, but I think this allows for a lot of heuristics. So you instead of verifying all the paths, there should be some heuristics of which path you verify first. And this could possibly improve the performance of the algorithm. So this is what we're thinking. But yeah, I will definitely look at the Cubitt work. Thank you.
The flip question is if you disallow the time dependence of the rates, and you because some people call Markovian things which are only
yes, of course,
a stationary
yes.
Could you solve that as well?
I don't think so. No, I mean, sorry. I mean, maybe I can, but not with this thing here. And the reason is, look like those optimal stuff that we are doing here is exactly like going from here to here is one Lindbladian, going from here to here is the other Lindbladian, going from here to here is the other Lindbladian, because this is like couple levels 1 and 3, then 2 and when they are all coupled at the same time, it's much more complex. It's very messy then.
Yeah,
it's much more messy. Yeah, thanks.
Right. So if we can have more questions offline after we stop recording.
Thank you.
But in the meantime, let's thank Kamil again.
Thank you. So I can, I guess,